Hello, it's Ben Holken. I'm recording this session for the benefit of researchers that may be using Simcenter for modal analysis purposes. So I have brought in a previously recorded set of measurements. In this case, we've done some measurements on the multi-axis simulation table using a laser vibrometer to complete a cantilever beam modal analysis. So we've done 6 measurement points on the length, along the length of the cantilever beam. Relatively small number of points, but this is not the purpose of the exercise to do a very detailed cantilever beam analysis. I have within this project, once it's opened, several sections of which we can select one. This section has 6 measurement runs in for the scenario where we had no laser vibrometer base motion, and a further 6 runs for the scenario where we had some base motion in the same direction as the laser vibrometer. So we're interested primarily, initially at least, in these first measurement points, or the first 6 runs of data, one for each of the 6 points along the length of the laser beam. What I ought to do is at this point show an image from the measurement campaign. So if I go back into my Teams folder, 6 degree freedom LDV mast project, I can in fact perhaps show the video, or a video of the measurement campaign. While that's loading in streams, I can maybe just have a look at one or either of these JPEGs, which will hopefully, show the experimental setup. So here's my laser vibrometer, modal shaker down here. We've got a force transducer, an accelerometer, and impedance head connected here. Laser beam is currently pointing at the top point on the beam, but it moved down into 6 separate locations. In fact, we started for run 1 at the bottom. Run 2 was at point number 2. Run 3 at point number 3, 4, 5, 6. The positions of the points on the beam are actually noted on the back side of the beam. We moved the laser beam using the scanning unit and the bespoke scanning head, just adjusting the voltage to one of the galvanometer mirrors to reposition the laser beam along the length of the beam at these 6 different points. It's a cantilever beam setup, so it's clamped underneath the mast table here to the structure, so it should have shapes that are synonymous with a typical cantilever beam bending scenario. Maybe that video is now loaded. Indeed it has. So if I play that full screen, hopefully the sound comes through. You can hear that the motion of the mast. If so, play it again. Play it again, Sam. So the vibrometer is, in this case, vibrating along the optical axis. It's only a relatively short video. The beam is being vibrated by the shaker up here, so it's a burst random excitation, and it's synchronized acquisition using Simcenter modal analysis. So the output from the laser vibrometer via the coaxial cable, as well as these measurements from compensation transducers that you can see here, and there are 2 other compensation transducers, are all being recorded simultaneously along with the outputs from the impedance head. The acquisition system is providing a voltage signal to drive the shaker, which has got an inbuilt amplifier. So that's the full description of the experimental setup. Back to Simcenter. So we have these 6 measurement runs within this base motion section. These are without any base motion vibration, so prior to turning on the mast, as I was showing in the previous video. We can highlight those, each of those runs. Within each run we have a series of functions that have been captured during the acquisition. We specified which functions we wanted to capture. We've got a coherence function, which is a commonly used function. We've got the FRF, which is what we need to be able to perform the modal analysis. We've got, I beg your pardon, if I go back here, reference autopowers, reference spectra, so they're complex spectra. The last one of the averages, the last time measurement, response autopowers. So we've defined a reference, that's the force transducer that's connected to the end of the stinger just prior to the beam. It's part of the impedance head. And then there are as many response measurements as we've defined. So we've got the laser vibrometer itself measuring in the Z direction. This is improperly labeled, the X direction here for the Y accelerometer, the Y correction accelerometer, and that's the accelerometer on the beam in the impedance head. So there's the force transducer in the beam, and there's the accelerometer mounted in the impedance head in the beam. Within each run we can have a look at the properties. So some of the project attributes are saved over. That doesn't look as though there's much information in there at the moment, but I can have a look at these archived settings within each run, and here's a lot of information, I hope. So if I blow this up, you can see it's the measurement run. Oh, that's disappointing. We've only got the creation timestamp. If I actually have a look at, let's say, the FRF, so between the laser beam and the force transducer, let's say, here we must have some more properties. Let's have a look at the properties in here. Yeah, okay, so there are a few more properties telling us which channel name it was measured on, the channel ID 3, the driving point, the frequency resolution, the type of FRF estimation method that was used, H1, H2 and HV are the options. Hardware range on the acquisition system was 3.16 volts. Any offset that was applied, there wasn't an offset. Lots of information contained in here, point direction, point ID as we specified in the channel setup, reference actual sensitivity for the transducer. This is the nominal sensitivity for the force transducer. That's the reference transducer, and the response transducer will similarly have a sensitivity somewhere. A bit unsure why it's not in that list, but it certainly will be in the list from the response auto powers and spectra. So if we go to this one, have a look at the properties here, we will see that the sensitivity surely is captured in here. I'm not seeing it. Actual sensitivity there, 20,000 millivolts per meter per second, and so on. So all of those properties exist at each of the functions, level of each of the functions. We have the last time trace, so we can explore the nature of these using these windows in Simcenter. So if I right click on this window and make it preview mode is useful. It uses the back axis to show us whatever it is that's highlighted in the display at any one time. One thing about the preview mode for time data is that we should show time data in a real format. So as you can see, if I switch to real, I now see a sensible looking signal. This is a burst random excitation as measured. That's the response measured on the impedance head. The measurement from the LDV, notice that the scaling is auto scaling as I select different measurement devices here. There was no base motion in this case, so these transducers should be showing a very small level. The mast itself isn't vibrating, but the LDV measures the response of the structure in velocity, the units of velocity. The beam accelerometer measures the response at the measurement point in G, of course, because it's an accelerometer. We can do an integration of accelerometer signal to velocity. It gives us a few options which type of integration method. This is doing a numerical integration for a time series data, and how many times we want to integrate, once or twice. If we want to go from displacement or acceleration to displacement, of course we can integrate twice rather than once. If this plot was frequency domain data, it would not apply any of these methods to that. It would do a frequency domain integration, so a j-omega integration or differentiation, in fact, if we were to use the differentiation option. These are just quick functions that you can process online. For proper processing of these data, we can do those also in here, or we can export to MATLAB and we can process those offline. So just a couple of more points on visualizing these data. Let's have a look at, for example, some of the other functions. Coherence functions and spectra might be better off presented on a Bode plot. Coherence less so. Coherence doesn't have any phase. We could have a look at the coherence functions. I'm back in the wrong plot. Let's thought this one was in preview mode. So that okay, it wasn't in preview mode. There's a coherence function between the accelerometer and the force transducer. Not a very nice looking coherence function. That's a bit of a better looking coherence function between the laser vibrometer and the force transducer. The FRFs, we can see those here, so these should be some good looking FRFs. We're just looking at amplitude only here. Decent peaks, a little bit noisy, a bit grassy down in the noise floor. A little bit better looking for the vibrometer, and we can continue to interrogate these plots in this way using Simcenter. So that's an introduction to the nature of the project, how we can investigate these functions within the Navigator, how we can preview them. There are lots of options to plot them. Probably I should show the Bodhi plot as a preview mode. And there you go. So now Bodhi plot preview mode, we can change the limits on this axis to log, and phase is displayed down here. So phase, remember, doesn't really have a meaningful value except as we pass through a resonance. So I've just right clicked on the display to put a cursor on here. I can get that cursor to snap to values, and then I can browse around here. If I select the curve with a left click, wherever the cursor is, I will get a readout on the data itself to show me the level. I can right click on the cursor and make a calculation. For example, if I had double cursor on here, I could do an RMS calculation. I can actually right click on the white area here and turn on an automatic cursor legend. So now if I have multiple cursors in here at different peaks, for example, I can also put an automatic peak on. It will similarly find that particular point. I can right click and remove all cursors, put an automatic peak cursor back on, put another single cursor on here, and as you can see, every time I put more cursors on, my cursor legend starts to show me more information. Snapping to data values is sensible so that it's not interpolating between values. I know that I've only got excitation in this case up to 100 Hertz because I specified that in the measurement campaign. I'm trying to double click the axis system here to be able to change the limits. I think that seems to have done something that I shouldn't have done because it's now giving me a hard time. So there's a window open somewhere that is preventing me from going further. I can change the axis system to get a finer view, more detailed view on these data. But at this point I'll stop the video and save this, and then we'll continue in a subsequent video to look at more of these kinds of things in Simcenter Testlab. Thank you.